in electrostatics topic, the one topic that is we will discuss now, that is the work done in an to build an electrostatic system. To build an electrostatic system, what will be the work done? Now consider that there is nothing initially. Now we consider that from infinity we are bringing some charge and put it somewhere here. It is Q1. Okay, but initially there is no charge. Around that point I take this charge from infinity and put it at any point in space. What will be the work done in bringing that charge? What will be the work done in bringing that charge? 0. Means there is no charge previously present at that point, such that who will oppose the movement of this charge. As a result, there will be no electrostatic work done to bring the first charge from infinity to a point in space. Okay, so I can consider that for this the work done is W1 and that is equal to 0. Then after placing this charge, we consider that from infinite distance I bring another charge and put it here at point this one, which is Q2. Second charge is taken. Now there is work done. Why work done? Because the field of the first charge opposes the presence of the second charge. We consider all the charges positive. So whenever you will place this first charge Q1 here, it will create its own field. So if you try to bring another charge from infinity and put it here, this first charge's field will oppose. So it will exert a repulsive force, and against that repulsive force you have to move it and put it there. Means you have to do work. You have to do work. Now the work done will come, and let us consider this distance is defined by R12. R12. So we can define this work W12 equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. You can consider that at the position of Q2, first charge actually produces some potential. What is the potential at the position of Q2 for the first charge? It is 1 by 4 pi epsilon naught Q1 by R12, and then that potential is just multiplied by the new charge Q2 to get the work done. That's why we can define that work done equal to potential into charge, or potential can be defined as work done per unit charge. Because if you calculate W12 divided by Q2, that is work done per unit charge, and that is equal to 1 by 4 pi epsilon naught Q1 by R12, which is the potential produced by this charge at this point. Clear? So from this you can already write this notion that work done per unit charge is the electric potential of a point. Work done per unit charge is the electric potential of a point. Okay. Clear? Now I will try to bring one more charge from infinity. And suppose I want to put it here. It is Q3, such that this distance is now defined as R23 and this distance is defined as R13. Now to bring the charge Q3, what will be the work done? What will be the work done? What will be the terms in work done? Two terms or one term? Two terms. Because when Q3 will come, previously how many charges are present? Two. So both field will oppose the movement of Q3. So you have to do work against both the fields. The fields of charge Q1 and against the field of charge Q2. So now we can write two terms in work done. One is W13, another is W23. Then it is 1 by 4 pi epsilon naught. First term will be Q1 Q3 by R13. Second term will be 1 by 4 pi epsilon naught Q2 Q3 by R23. Okay, Q2 Q3 by R23, same as before. For the first charge, there is no charge previously present, so no work done. For the second charge, first charge is already present, so there is a term in work done. For the next charge, third charge, previously two charges are present, so you have to calculate two work done. Similarly, in this manner, if I take the fourth charge, we have to calculate the three terms in work done. Now, I am considering this three charge system only. Then, what will be the total work done in building this system? Sum of all the work, because work done is equivalent to energy, which is a scalar quantity. Scalar quantity means simple addition will give you the total work done. So total work done will be, in preparing this three charge system, will be sum of all these three. W. All these three has to be summed. So 1 by 4 pi epsilon naught is taken common, and you can write this one as Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23 entire. So similarly, if there are 4 charge, 5 charges, we can calculate all the work done. It is just the sum. For each and every charge, you have to calculate the interaction with all the other charges and calculate the sum. This is the procedure to calculate the work done. Okay. Now, this is called also the electrostatic interaction. Electrostatic interaction energy. Because this work done is stored in the electrostatic system as its potential energy. Because if external agent is doing work, then potential energy is stored in the system. So this work done is stored in the system as its electrical potential energy. The same idea is utilized in case of charging a capacitor. Because there is an uncharged conductor, you are putting charge one by one. So when you put the first amount of charge, there will be no work done. Then when you try to put the further charge, the first charge previously present will repel this one. So you have to do mechanical work. And as you do mechanical work, to put this charge over, the electrostatic potential energy of the capacitor will increase. Clear? So write down. If external agent is doing work, in placing an amount of charge, in an electrostatic system, then electrostatic potential energy of the system will increase. Electrostatic potential energy of the system will increase. Okay? Now, from this concept and the other part that is left in the chapter, that is the calculation for the dipole. I have already calculated the one case, that is the electric field for a dipole on the perpendicular bisector. On the perpendicular bisector, it will be Kp by r square, r cube, Kp by r cube, and on the axis it will be 2 Kp by r cube. Okay. Now we want to electric field for a dipole at any arbitrary position, Okay. See, if you try to find this calculation in your book, then in the many books it is written as radial field is one component, another component of the field is transverse component, and they calculate it. But this calculation is actually coming from the calculation of the potential. First you have to calculate the potential for the dipole at any arbitrary point, and then accordingly by differentiating the potential you have to find the electric field, because yesterday we discussed that part, that negative derivative of potential is electric field. So from that negative derivative it will come. But since we are in this type of case, we have to use the polar coordinate. So in that polar coordinate, derivative is something different, not like that in Cartesian coordinate that we have find Ex equal to minus del v del x, we have written Ey equal to minus del v del y. But in case of polar coordinate, the form is not exactly same, it is different. So we will just consider the potential function directly, because the derivation is not at all required for this NEET exam. So we are not going to the detailed derivation of the potential at any arbitrary point for the dipole, because for that too many calculation steps will be there and it is not required for your exam. You have to remember the potential function, which I will write directly. See, let us consider these are 2 point charges, minus q plus q. This is the dipole axis. Now from this midpoint there is an arbitrary point here. Where it goes? This is the arbitrary distance r, and we can consider that from the dipole center this angle is theta. Theta is taken in this direction. So at this point, if I calculate the potential first for at this point, okay, this is completely arbitrary point, neither on axis nor on perpendicular bisector. So at this point the potential function will be this one, QD, D is this distance, dipole length, cos theta by 4 pi epsilon naught r square. Now remember one thing, that for the dipole potential varies with 1 by r square. For a point charge potential varies with 1 by r. Clear? Similarly, for the dipole electric field varies with 1 by r cube, where for point charge electric field varies with 1 by r square. There is a difference in power for the field and potential for a point charge and for a dipole. Okay. Now, in this case, this potential is QD cos theta by 4 pi epsilon naught r square. Detailed derivation is in the book, but I am not going to the detailed derivation of this formula. There are too many approximation step, binomial approximation, and all these things have to be there. Now, for this, just consider potential. Is it a one-dimensional potential or it is two-dimensional potential? See how many coordinates are involved in potential. Previously, yesterday when we discussed this problem, that suppose V is given x square y plus y. This potential, it is two-dimensional because x and y, two terms are there. So it is a function of x and y both. So it is a two-dimensional potential. If it is only x square, then it is one-dimensional potential. And if it contains x, y, z, then it is called three-dimensional potential. So in this case, how many coordinates are involved in this case of dipole? Two. One is r, another is theta. That is the polar coordinate. So r and theta both are taken as dimension. So it is two-dimensional potential. So for finding the electric field from this problem, what we have done, we written that Ex equal to minus del V del x and Ey equal to minus del V del y, and calculate the electric fields x component and y component, and then we write E equal to Ex I cap plus Ey j cap. Okay, just once see the yesterday's problem in your copy. It is, just see what we have done. From V we calculate Ex, Ey separately by taking the partial derivative and then put in the vector form, Ex I cap plus Ey j cap. The same procedure we try to apply here. And once we are differentiating with respect to x partially, means y remain constant. Okay. Similarly, when we are differentiating with y, x remain constant. The same technique has to be used in polar coordinate. But then two component of E I should write. One is ER, that is called the radial component of the electric field. That can be written as minus del V del R. Similarly, other component is transverse component, that is E theta. This should be minus del V, not del V del theta. That is the difference between Cartesian coordinate and polar coordinate. ER has the same form, that is minus del V del R, but E theta is not minus del V del theta. See why. Del V, if you consider this del V means change in potential. So what will be its unit, SI unit? Volt. Del X means change in distance along x axis, that is in meter. So its unit will be volt per meter. What happened? Automatically italics are taken. Hey, how to take it back? Bring it back. This one. Oh, this one. Huh. Is there any problem in calibration? Okay. Now, see, its unit will be volt per meter. Okay. Similarly, for del V del Y, it is again, del V means change in voltage, so its unit is volt. Del Y, change in length along y axis, that is also in meter, so it is also volt per meter. And you know that electric field has the unit volt per meter also. You can write it Newton per coulomb or volt per meter. Now check, what is the unit of E del V del R, that is ER. Del V is again volt. What is del R? Change in length along the radial direction, along the radius. So that is meter. Calculate its unit. Volt per radian, not dimensionally matching. Del theta means change in angle, and in polar coordinate this angle is taken in radian. So volt per radian is not the electric field. Volt per meter is the dimension of the electric field. So in polar coordinate you cannot write simply as that of the Cartesian coordinate. ER will match, but E theta will not match. Okay. So this form of E theta is not true. This is actually minus 1 by R del V del theta. That is the correct form of E theta component. Now see, radian means a dimensionless. Radian has no dimension. Because why we consider angle in radian in SI system? Because radian means ratio of the two length. So it has no dimension. So instead of writing this radian, now I can easily write, since there is one R, it is again volt per meter. This radian has no dimension, so del V has the dimension of volt, unit of volt, and this 1 by R is there, so R is the unit, R has the unit meter, so it will be again volt per meter. So remember always that in polar coordinate E theta component is minus 1 by R del V del theta, not just minus del V del theta. This is the only difference between Cartesian and polar coordinate. Okay. Now we can calculate easily the electric field's radial component from this ER. QD means P, that is dipole moment vector. So I can write D del R I can write this one as del R of P cos theta by 4 pi epsilon naught R square. Okay. QD means P. So P cos theta by 4 pi epsilon naught R square. Now, which of the terms are common? P is constant, so I can take it outside. Cos theta is also constant because we are differentiating with respect to R. In partial derivative, other variable is taken as constant. 4 pi epsilon naught is also constant, so we can write this one as P cos theta by 4 pi epsilon naught. These are be taken out. Then remaining term will be del R of r to the power minus 2. What is derivative of r to the power minus 2? Minus 2 r to the power minus 3. Okay, minus 2 r to the power minus 3. So this one will become p cos theta. There is this one. There is inbuilt minus there. See. So this minus will become plus and it will be 2 by 4 pi epsilon naught r cube. R to the power minus 3, that can be written as 1 by r cube, and there is a minus 2 in front, minus 2 and this minus, this product will be plus. Because see, E is minus del del r of V. Negative derivative. Okay. So that term will give you minus 2 by r cube. So just multiply with this minus, it will become plus and it will be 2p cos theta by 4 pi epsilon naught r cube. This is the ER component of the electric field. Okay. Is that calculation clear to everyone? Now we want to calculate E theta part. See. This one. So E theta can be written as minus 1 by r del del theta of the entire term. Entire term is p cos theta by 4 pi epsilon naught r square. Okay. See, p by 4 pi epsilon naught r square, all are constant except cos theta, because now we are differentiating with respect to theta. So except theta, the other variable and all the constants can be taken as constant term. So I can write this one as, now tell me, if these constants will count, then it will become p by 4 pi epsilon naught r cube, because there is a r square, there is another r, and derivative of cos theta minus sin theta. So it will become, this minus will become plus and it will be plus sin theta. So p sin theta by 4 pi epsilon naught r cube. Okay. P sin theta by 4 pi epsilon naught r cube. That is called the radial component of the field. This is called the transverse component of the field. That is E theta. Like Ex I cap plus Ey j cap. Similarly, I can write Er r cap plus E theta theta cap. This is the complete electric field for the dipole at any arbitrary position. Okay. Now, if someone asks you to calculate the magnitude of the field, calculate the magnitude of the field, what you will do? Simply I have to take these two terms, that E square will be equal to Er square plus E theta square. Er square equal to E square equal to Er square plus E theta square, because these two components are perpendicular to each other. Like Ex I cap plus Ey j cap, what is E square then? Ex square plus Ey square. Now If you calculate this one, you will get first term. See, this one will be 2p cos theta by 4 pi epsilon naught r cube its square. Next term will be p sin theta by 4 pi epsilon naught r cube its square. See, can I write this one like this? P by this is taken as common. See, p square will be there, 4 pi epsilon naught r cube, entire square will be there, so it can be taken common. So what are the remaining terms in this bracket? 2 cos theta whole square. 2 cos theta whole square means 4 cos square theta. And that is sin square theta. Sin square theta can be written as one minus cos square theta. So E can now be written as P by, just take a square root, 4 pi epsilon naught r cube into 3 cos square theta plus 1. You have to remember this last formula. Electric field at any arbitrary position, its magnitude. This one. If you can remember this formula, then you can calculate the electric field for any distance at any angle. Okay, because we derived it for an arbitrary position like this. This is the dipole, minus q, this is plus q at any arbitrary point r, this is the theta. At this point we want the electric field. Now think of it, if it is on the perpendicular bisector, then what is the value of theta? 90 degree. Theta should be 90 degree, then it will be on the perpendicular bisector. Put theta 90 degree and check whether the value you know that is coming or not. Cos 90 will become, so this quantity will be root 1. Root 1 means 1, so it is coming P by 4 pi epsilon naught r cube. That is the electric field for the dipole on the perpendicular bisector. On any axial position, if you calculate, what is the value of theta? 0 degree. Just put cos 0. Cos 0 will be 1. So it will be 3 plus 1, 4. Root 4 is 2. So it is 2p cos theta by 4 pi epsilon naught r cube. Both the formulas will come directly from, if you remember this one. And it will be helpful in other angles also, because if you know only the perpendicular bisector and on the axis, then for arbitrary point you cannot calculate. But if you know this general formula, you can calculate for any angle. Even the special cases of field on the bisector and axis can be calculated from this formula. Okay. Now there is one topic is there, that is the when an electric dipole is placed in an uniform electric field. Placed in an uniform electric field. So that topic we have to discuss. A dipole in non-uniform field is not in the syllabus. See, if there is any electric field, I consider the electric field is along this direction. Electric field is directed along this, and in this electric field is uniform E along the x-axis, and in this electric field we consider that I place an electric dipole like this. These are the charges minus Q and this is plus Q. Okay, so this is an electric dipole having this length D. Clear? This dipole is placed in an uniform electric field. Now, first we will calculate that dipole means a combination of two equal and opposite charges. So each charge will experience some force when placed in an electric field. Now first charge will feel a force in which direction? Positive charge, along the direction of the field. So I will draw that. This first charge will experience a force along this direction, and its magnitude will be Q times E. Okay. Second charge will experience a force along this direction, and its magnitude will be same, Q times E, but direction is opposite. So positive charge is feeling a force along the field, negative charge of the dipole is feeling a force opposite to the field. So what is the tendency of this force? What is the net force? First tell me, what is the net force on the dipole? 0. But their line of action is not same. That's why they will produce a torque. And as a result, this dipole will rotate and it will be aligned in the direction of the field. So this torque will try to restore the dipole or align the dipole along the direction of the field. Means dipole distance or dipole moment vector will be along the direction of the field, not in the opposite direction. Because if it is like this, so this white tip is considered as the positive charge, this one as the negative charge. So due to this force, this torque, it will rotate and align itself like this, not in this orientation. It will be oriented along this. Okay, so if it is oriented along this, means this is positive, this is negative. So dipole moment vector is directed from negative to positive. So dipole moment vector and direction of the field will be same. So this torque has a tendency to align the dipole along the direction of the field. Clear? Now, if you release the dipole from this position, still it will rotate it in this direction, still it will rotate. So in all orientation, if you place it like this, like this, like this, it will orient the dipole like this. Only one case is there when it cannot be oriented in the direction of the dipole, in direction of the field. If it is exactly placed like this, then it is not oriented, dipole moment is not directed along the field. Here dipole moment is directed opposite to the field. Because in this setup, torque is not created. Torque will be created only if it is at certain angle. Because we know that, what is the formula for the torque? R cross F. That is Rf sin theta will be there. Okay. Then if theta is 0 or 180, can the force produce torque? No, because sin 0 is 0, sin 180 is also 0. So if the dipole is already like this, then electric field and dipole moment both are along the same direction. So angle between them is 0 degree. So their cross product will be 0. So torque will not be created. Similarly, in this orientation, Dipole moment and electric field are 180 degree apart. So again sine 180 degree will become 0. So no torque will be created. Only in this setup torque will be created, and torque will always try to rotate the dipole in this orientation, not in this orientation. Clear? So torque will only try to align it with the field, not to align it opposite to the field. So write down, torque produced on an electric dipole, torque produced on an electric dipole in a uniform electric field in a uniform electric field will always try to align the dipole moment vector, always try to align the dipole moment vector along the direction of the electric field, along the direction of the electric field. In whatever configuration you will release the dipole with some angle, non-zero or non-180 degree angle, it will definitely align the dipole along the direction of the field. This is the property of this dipole. Now, from this a very good question will come. One is that first case, suppose electric field is given along this direction. In the second case, electric field is also along this direction. Same in both the cases, an uniform field. Both the cases, same field. First time the dipole is given like this. This is D, the dipole moment vector. This is minus Q, this is plus Q. In the second setup, this is minus Q, this is plus Q, then this one is D. This is setup 1, this is setup 2. In which case dipole has the minimum potential energy? In which case dipole has the minimum potential energy? Or in the both the cases it has the same potential energy? What is the net force on the dipole in the first case? Net force on the dipole in the first case? 0. Second case? Net force again 0. See, in the first case, positive charge will feel the force along the field, negative charge will feel the force opposite to the field. So the forces are like this, but they are equal in magnitude and opposite in direction. So net force on the dipole in the first case is 0. See, in the second case, positive charge is feeling a force along the field, negative charge is feeling a force along the field, opposite to the field. So now the forces are towards each other. Previously forces are away from each other. Net force 0. Now forces are towards each other, but still net force is 0. So net force on the dipole in both the cases are 0. Previously they are opposite from each other, now they are towards each other. But in each case vectors will cancel. Now, if you talk about the net torque, in the first case what is net torque? 0, because line of action of the forces are along the same straight line. In the second case torque is also 0 along the same straight line. but still torque is 0, force is 0 in both the setup, but one corresponds to minimum potential energy, other corresponds to maximum potential energy. How? See, this white tip is considered as the positive charge and other portion is taken as the negative charge. So now it is oriented here. You slightly displace the dipole, disalign the dipole like this. What will happen? Torque will act and it will rotate the dipole along the direction of the, in this direction, such that it will be aligned to the field. So if you disturb this one, always this torque will align the dipole along the direction of the field, whatever be. Now consider this setup. Positive charge is now here. You will slightly disturb the dipole. What will happen to the dipole? Will it come back to the same position or will it completely reverse the position? Completely reverse the position, because this torque has, according to that equation, that diagram, the positive charge, if you disalign, positive charge will feel the force along this, negative charge will feel the force along this. Completely rotate the dipole and align it such that its positive charge is here, negative charge will be there. So it completely changes the orientation. See again, in this setup, normally when you keep it here, so positive charge will feel force along this, negative charge will feel force along this, dipole is rotated like this. Now in this setup, positive charge is already here. If you slightly disturb, positive charge will feel the force, negative charge will feel the force, it will align, it will align, it will align always. But here positive charge is here. If you slightly disturb it, positive charge will feel force on that direction. So it will align the dipole completely in opposite direction. So second case is that maximum potential energy configuration, and first case is minimum potential energy. First case corresponds to the stable equilibrium. Second case corresponds to unstable equilibrium. Unstable equilibrium means maximum potential energy. In both the cases, torque, force both 0. But if you disturb it, it will definitely in this setup come back to the initial condition. But if you disturb it from this condition, it will never come back to the initial condition. Like this one. Just a normal pen, give me a normal pen. See, this pen, if it is kept on this table, it is at rest, net force is on this pen will be 0, net force on the pen will be 0. Now, if I slightly disturbed it from its equilibrium position, see, it will always come back to the same condition, means horizontal. Now consider that this pen is very difficult to keep this pen like this. Okay, this is not exactly the same, little bit more flat surface is required. It may happen that the table is not properly aligned, not perfectly horizontal. Okay, see, let's do it with this pen. Okay, the same situation with this pen also. If it is there, if I disturb it, it will come back to the same horizontal position. But this is also at the rest condition. Rest condition means net force on this will be 0. But now slightly disturb it from its equilibrium. Can it come back? It will go back to the other position. So this one is the unstable equilibrium condition and this one is the Stable equilibrium condition. Now see, you can consider that entire mass of this pen is concentrated at its center of mass. So where is its center of mass? Just at the midpoint. And if you consider entire mass at the midpoint on the axis, then what will be the distance from this stable surface? This much. Now when you place this one, center of mass is here, but its height from the base of the table will increase, means potential energy MGH will increase. So it has the maximum potential energy. So maximum potential energy means unstable. If you disturb it from that position slightly, it will orient itself to the minimum potential energy configuration. The same thing happens to the dipole. In this setup, it has maximum potential energy. If you slightly disturb it, it will orient itself like this. But here it is the minimum potential energy. If you disturb it slightly, it will come back. Okay. So write this one. First case is the minimum potential energy configuration for the dipole. Minimum potential energy configuration for the dipole. Draw the two cases and then write. Minimum potential energy configuration for the dipole, that is stable equilibrium condition. Second case corresponds to maximum potential energy configuration, that is unstable equilibrium. So sometimes this type of two diagrams are given and it is asked in the combination that in the first option it is given that whether in both the cases force 0, torque 0. In both the cases, first case force 0, torque not 0. Second case force 0, torque 0. This type of combinations are given in the options and you have to find out the correct option. In these two orientation, suppose option A is force is 0 and torque is 0 for both the cases. Second option is force 0 but torque not 0. Third option is force not 0, torque 0. Fourth option, neither of them is not 0. Force is non-zero, torque is non-zero. So this type of four options are given. You have to identify the correct option. So in this setup, force, torque both 0. But one corresponds to stable, one corresponds to unstable. That's why maximum and minimum potential energy will come. Okay. Now, two more formulas you have to remember from here. One is when this kind of a dipole is present in the field, the torque formula. That is, this torque on the dipole will be equal to P cross E. That is, magnitude of the torque is PE sin theta. And work done by this torque is PE P dot E, and it can be written as PE cos theta, and corresponds to that potential energy can be written as minus P dot E, minus P dot E. But remember, always minus P dot E will not give you the correct answer. Normally written in the book that minus P dot E is the potential energy, but this will not give you the correct answer. Why? There is one question in your one of the mock paper. It is related to the magnetic field, magnetic dipole, work done by potential energy stored in a magnetic dipole. Same thing, P dot E, instead of P dot E you are using minus M dot B, but it will not give you the correct answer. MB cos theta if you are using, not give you correct answer. Why? Because when you are calculating this work done or potential energy, you have to put the two limits, that it is oriented from an angle theta 1 to an angle theta 2. So you have to take the other limits, and in this calculation when we write P cos theta, we consider when it is at 90 degree potential energy is 0. But unless it is specified, you cannot consider that it is 0. So that's why better to use this one. U will be PE cos theta 1 minus cos theta 2. It will always give you the correct answer between the two angles. No need to say that theta 1 is, because from this formula, if you consider that theta 1 is 90 degree, and at this setup when theta is 90 degree, that is the dipole moment and electric field are perpendicular to each other, then theta will be 90 degree, and they consider that at this moment potential energy is 0. But if it is not mentioned in the problem that at that moment potential energy is 0, then your calculation will not give you the correct answer. So that's why it is always better to put the limits from the calculation, and then accordingly whatever be the angle, just put it in this equation, you will always get the correct answer. Because at angle 90 degree potential energy is 0, no need to remember that, because if you put theta 1 90 degree, cos 90 will be automatically 0, then it will be minus PE cos theta 2, the final angle. So always remember this angle. The same formula you should use in magnetism also, because in magnetism it will be just same replica of this formula, MB cos theta 1 minus cos theta 2. Always give you correct answer if you put the two angles. Okay. So don't write directly P cos theta or P sine, P cos theta and MB cos theta like this. What is capacitance? Ability of a conductor to store charge. How much charge a conductor can store. Now, there are some factors on which capacitor of a conductor depends, and if I have one conductor, say, then if you give some charge, if you put some charge to this conductor, suppose Q, charge is given to the conductor, then its potential will increase. That means amount of charge and potential of the surface of the conductor are directly proportional. So if you give more charge to the conductor, potential of the conductor will increase more, will increase. Okay. Now, there should be some proportionality constant. Proportionality constant is taken as C, called the capacitance of the conductor. So we can write Q equal to CV. C can be written as then Q by V. Now generally in SI unit, Q is measured in coulomb and V is measured in volt. So I consider that if 1 coulomb charge is given to a capacitor and its potential of the surface increases by 1 volt, then 1 coulomb by 1 volt is the capacitance of that conductor, which is considered as 1 farad in SI system. 1 farad, that is 1 coulomb by 1 volt, that is called 1 farad. Now if I ask you on which factors C depends for a conductor. Suppose we have two different conductors, so capacitance will not be same. So on which factor this C depends? Means if you change some quantity, the C will be affected. So what are those factors? What is in this equation? So if you change Q, then C will change, C will affected, and if you change V, C will be affected. Because C equal to Q by V, so if I change Q, then there is a change in C. If you change V, there is a change in C. No change. If you change Q or V, they are directly proportional. So, and proportionality constant is C. So C is not depending on Q and V. So don't expect that if the formula is C equal to Q by V, so C depends on Q and C depends on V. Okay. So this has a mistake. So don't do it, because you mentioned C as a proportionality constant. So it will not depend on the variables involved in this equation. So write it. C is not depending on Q and V. It can depend on other factors, but never on Q and V. So on what factor they depends? Which energy? Dimension? Correct. One is dimension. Dimension, the term is not exactly correct. That is called the curvature. Curvature is correct. First one, write down surface area of the conductor. Number one, it depends on surface area of the conductor. Okay. Number two, curvature of the surface of the conductor. Curvature of the surface of the conductor. Okay. Number three, presence of a dielectric medium. Presence of a dielectric medium around the conductor. Okay. Number four, presence of a conducting medium around the conductor. Presence of a conducting medium around the conductor. Means one conductor is there whose capacitance is to be determined. You put another conductor close to that. Then the first conductor's capacitance will be affected. Instead of that, if you put dielectric, then it is also affected. If you change the curvature of the surface area, then it is also affected. Now, why it depends on the area? Simply we can say that charge will be stored in the conductor and charge will be stored on the outer surface. So if the outer surface conductor is large, then it can store more charge. So capacitance will increase. So as area increases, capacitance will increase. How it depends on the curvature? Because you know that if there is a sharp curvature, just a point or a edge, more and more charges will be accumulated at that edge, corner point. Charge density will be too high. Charge density too high means charges are very close. So they will repel each other. And if there are many people, not 48, suppose there are 100 students in this room, what will happen? Near the gate, they will fight each other and push someone out. So the same thing happens to the conductor. Near the highly curved portion, the edges, the corners, the charges will repel each other too much. They are fighting too much and some of the charges are thrown outside the conductor. That is called the charge leakage. For the sharp points, the charge will actually leak in the air. So that is called the corona discharge. Okay. Now, due to this, actually the conducting material loses the charge if there are sharp edges or corner points too much. So that's why flat conductor always containing more charges, its capacitance will increase. So if the curvature increases, the capacitance will decrease because charges are pushed out of the conducting surface. Then if you put a dielectric, what will happen? In the dielectric, if you put the dielectric will decrease the electric field and decrease the surface potential. In that case, what will happen to the conductor? You can supply more charge to the conductor to increase its potential. Suppose the conductor has an ability to store charge until its potential becomes 10 volt. A conductor is there, its surface potential is 10 up to 10 volt, it can store charge. After 10 volt, if you put certain charge, what will happen? It will be discharged. Some charges will be left out. Now, if you put a dielectric material instead of air, suppose glass slab or wooden slab is placed around it, what will happen? It will decrease the electric field and electric potential of the original conductor. So suppose it goes to 8 volt. Now how you can supply more charge such that its potential could be increased to 10 volt again. So it will contain more charge. So initially 10 volt is there. When around surrounding medium is air, it contains certain amount of charge. More than 10 more charge it cannot be given, because if it is potential is increased from 10 volt, charges will be discharged. So maximum ability of it to create a surface potential of 10 volt with a certain amount of charge. Now you put this conducting rod around a dielectric, that is wooden slab. So since it is a dielectric, the electric field and potential on the surface of this conductor will now decrease, suppose to the 8 volt. Then it has now gaining the ability of taking more charges such that its surface potential can be again increased to the 10 volt. So to increase the potential by 2 volt, some additional charges to be given, so capacitance will increase. Similarly, if you bring another, instead of dielectric, another uncharged conductor, then its potential of the original conductor decreases much more. In that case, it will contain some more charges. Okay. So in this way, if you put the dielectric, then capacitance will increase. If you put an uncharged conductor in front of the original conductor, then capacitance will also increase. So these are the factors on which capacitance depends. So from this portion, only some theoretical question can come, that if something is given, whether there is an increase or decrease in the capacitance. So theoretical question can come from this, and these questions are very easy. Now we will go to the other calculations of the conducting material, for the conducting material. First, what is the capacitance for a parallel plate capacitor? Parallel plate capacitor. See, this is one plate. I consider it is infinitely extended. This is another plate. It is also infinitely extended plate. This one is carrying a total charge plus Q. This one is carrying a total charge minus Q. This distance is taken D, and each plate has area of cross section capital A. Now tell me, what is the electric field between these two plates? Because in the last class we discussed this problem. If the first plate is, one is positively charged plate, another is negatively charged plate, between the plates the field will be sigma by epsilon naught. So here the field will be directed along this, and its value is suppose E, and in the last class we derived this one, E equal to sigma by I can write this one as sigma equal to Q by A, total charge per unit area, that is sigma, surface charge density. So Q by epsilon naught A. Now consider that I have one positive charge, unit positive, I have one charge, say small q, or unit positive charge you can consider, plus 1. Okay, unit positive charge plus 1. And what I wish, and it is in front of the negative plate. So I can consider it like this, I will remove this charge from the negative plate and slowly moving it and put it on the positive plate, such that negative plate will be more negative and positive plate will be more positive. Then the charge once removed from the negative plate on its own will not go to the positive plate, because it's a positive charge. So field will repel this, it will exert the force in the opposite direction, such that electric field will try to put this unit positive charge again on the negative plate. So what you have to do, if you wish to move it to the positive plate, you have to apply force, that is you have to do the work done. So work should be done by external agent against the field to move the charge against the repulsion and put it to the positive plate. Okay, you have like this. So force is along this direction on this positive charge, and you are taking it and putting it on the positive plate. So against the field you have to do work. So that is external agent is doing work. So if external agent is doing work, this work is stored in the system as its potential energy. Because whenever external agent is doing work, suppose this marker is here, I am putting this marker over a certain height. So gravity is pulling it down. I am doing work against gravity to put it at a certain height. So who is doing work? Me. The gravitational potential energy will increase. The same thing, electrostatic force is on this unit positive charge downward. Against that force I am putting it up, moving it and put it here. So similar to that situation, potential energy of the system will increase. Here it is, previously it is, in this example it is gravitational potential energy, in this example it is electrostatic potential energy. Okay, now so you want to calculate this work done in moving the unit positive charge. Now work done by charge, that is equal to potential, work done by charge equal to potential. And if the charge is unit positive charge, then work done is itself the value of the potential, because W by Q is V. So if I put Q equal to 1, then W is itself V. So we can calculate the potential directly and claim that it is the work done. So I will calculate the potential for this potential difference. So this potential difference between these two will become electric field for the unit charge, E into this one. E is the electric field in this direction and distance moved is D. So E into D will give you potential difference. Or you can also consider that this is work done, this is force into displacement. Force into displacement is work done, correct? Then if you consider each charge, force is Q into E. Now if you consider this form, Suppose small q is taken, so small q, so this is force, this is displacement. Force into displacement is work done. If instead of unit positive charge I consider the charge is small q, then small q charge will experience a force in the downward direction, and that will be calculated by q into E. So QE is the force, and against that force you are moving. So by displacement D, so QE into D will give you force into displacement, that is work done. Now I am asking that if I put Q equal to 1, so this one will become ED and this one will become potential itself. So we can write V equal to E. E is the one, capital Q by epsilon naught A into D, and from that we can write Q by V, that is equal to epsilon naught A by D. This is the capacitance of the parallel plate capacitor when filled inside the region between the plate is vacuum. You can either consider that you are moving unit positive charge, or you can consider any arbitrary charge plus Q, then calculate the work done accordingly, or you can also choose unit positive charge from the beginning, whatever you wish. Because see, if you consider this one is plus Q, then force on this one will be downward, that is QE, and you are moving against the field, so work done will be QE force into displacement, that is work done. Now divide it by small q, so what will happen? W by Q, that is work done per unit charge, that is potential. Either start with this notion or directly consider that small q test charge is 1 and directly calculate the potential. Same thing. After all, you consider unit positive charge or you consider any arbitrary charge, you have to calculate the potential difference between the plates. If you calculate the potential difference between the plates, you can calculate the capacitance, otherwise not. Clear? So this is the parallel plate capacitor when entire part is filled with air. Now I will calculate from this the what is the stored potential energy, because I am doing external work to put this charge on that capacitor. So what is the energy stored that we want to calculate? So remember, this result is there. Now we will calculate this part. I will erase some portion of this. See, check. Now I will calculate one situation, and which is valid for all the cases. I will consider an arbitrary conductor. Okay, so in this arbitrary conductor, initially consider uncharged, and I want to put some charge on this conductor. So what will be some charge small q given to the conductor? So what will be the work done in doing that? Nothing, because there is no charge in the conductor. So conductor will not repel when you bring some positive charge and put it on the conducting surface. It will gladly accept. So you are giving certain amount of charge to this conductor Q. But once this charge is received by the conductor, there is a change in its potential. So surface potential on of the conductor will now V, and say the capacitance of the conductor is C. So we can write that Q equal to CV. Okay. Some charge is given to the conductor. It is initially uncharged. So no work has to be done for putting this first charge to the conductor, and it will become CV. Now in very small steps, I want to give very small amount of charge to the conductor slowly. What will happen? Now the conductor will not gladly accept any further charge, because if you put certain charge on the conductor, now the conductor is positively charged. If you bring another positive charge to put on the conductor, it will repel this one. So if you try to put this charge over the conductor forcefully, so you have to do work against the repulsive force. Okay, so external work should be done. So we want to do that. So we will put further charge dq to the conductor. Further charge dq to the conductor. So what is the potential of the conductor previously? V. Some dq charge should be put, then work done should be dw equal to dq into V. Work done should be dw equal to dq into V. That is work done per unit charge is potential. That is still maintained. Now I want to calculate this total work done until the charges is grows from 0 to capital Q. I want to increase the charge in the conductor until the amount of charge on the conducting surface will be capital Q to a very large value. Then you can write it is dq into, what is V from this expression? Q by C. C can be taken out of this integral because that is constant. So Q dq, what will be its integration? Q square by 2, and putting the limits, it will be capital Q square by 2 minus 0. So this work done will be Q square by 2C, and this work done is stored in the conductor as its electrostatic potential energy, because who is doing this work? External force, because you are putting this charge one by one. So external force is doing this work against the field. So potential energy of the system will increase, and it is stored in the system. So it will be Q square by, so further then we can write this one as U equal to Q square by 2C. U equal to Q square by 2C. And then once the conductor is gaining a charge capital Q, then we can also write this expression as capital Q will be equal to C into V, and putting this one here you can derive 3 more forms: half CV square or half Q into V. So all of the form can be taken as the stored potential energy inside the conductor. Either of the form you can use, but in regarding when we are solving problems, certain form will give us more advantage. Okay. Now from this we can calculate something from these two results. Now this calculation that we have done for the work done or electrostatic potential energy is equally applicable for this setup also, because that is considered as completely arbitrary setup. So this calculation is valid for electrostatic potential energy, for parallel plate capacitor, for spherical capacitor, cylindrical capacitor, for all type of capacitor. There is no such special case with the shape. That is a general calculation. Okay, so we will now use this general calculation of electrostatic potential energy to the parallel plate capacitor. See, that part is copied. Erase some portion of that part. Okay, see, this one I will use this form, U equal to Q square by 2C. Q square by 2C. But what is C for parallel plate capacitor? Epsilon naught A by D. I will put it here. Okay. So 2 epsilon naught A by D. Now you can write this one as U equal to Q square D by 2 epsilon naught A. Q square D by 2 epsilon naught A. Okay. Now from this one find Q. What is Q? Q can be written as epsilon naught A into E, right? Q can be written as epsilon naught A into E. I will just put the value of Q here. Okay, see what it gives. Q square is there actually. So epsilon naught square A square E square D divided by 2 epsilon naught A. Correct? Now I will cancel some term. Check. 1 epsilon naught will cancel. 1 A will cancel. Okay. So we are getting the term epsilon naught A is square D by 2. Now I want to write this one in this form. Capital U divided by AD half epsilon naught E square. Okay. Half epsilon naught E square U by AD. Up to this, is there any problem in calculation? Okay. Now, what is AD? AD means volume. See, this capacitor plate has area A and this distance D. So just if you consider the cubical portion between these two plates, it's just a volume having surface area A and distance D. So cuboid, what is the volume of the cuboid? Length into breadth into height. So same thing, length into breadth is area, area into height is volume. So A into D will give you the volume of this region. Now, U is potential energy. So it is potential energy per unit, that is pressure. That is the electrostatic pressure developed between the plates. So region between the plates, there is an electrostatic pressure. That is, its form is half epsilon naught E square. You can also call it electrostatic potential energy density between two capacitor plates. And still, see, this one is also independent of the particular shape. Half epsilon naught E square is there. There is no such things related to the parallel plate capacitor. Even this form is applicable for other types of capacitor. This is a general form. So half epsilon naught E square will give you the electrostatic potential energy per unit volume, that is the energy density, which is creating, actually energy density is itself called pressure. So it is also called electrostatic pressure between the two capacitors, between the capacitor plates. It may be spherical capacitor also. Okay. Now, if I ask you, there are two parallel plate capacitor and all these things, and you are doing some mechanical work in giving the charge, then you are doing mechanical work means potential energy is given to the system such that the system's potential energy will increase and it is stored in the system. Then where in the system potential energy is stored? In which part of the system potential energy is stored? In this case, means there are many things in the system, that is charge is there, plates is there, field is there. Where the potential energy is stored? Inside the charge or inside the field? Which store potential energy? Charges can store potential energy or electric field can store the potential energy? Only field, because field is related to electromagnetic wave. Electric field and magnetic field together produces electromagnetic wave, and wave carries energy and momentum with it. So electrostatic potential energy is stored in the field, not in the charge, because charge is not a mass. Charge particle has some mass, but charge itself is a property. It has not mass such that you can say half mv square. Like half qv square will not give you any kinetic energy. So it is stored only in field, and that is calculated, that is coming from this final equation. See, U by AD, that is charge density. Is there any term, electrostatic potential energy density, U by AD, is that containing Q? It is containing half epsilon naught E square. Means field is inside the field, only electrostatic energy will store. Okay, because more and more, if you consider this electric field, it is just like a electromagnetic wave. So electric field will have a wave-like structure that you have done. So if you put more energy, electrostatic energy, what will happen? Frequency will increase. And if you put less energy, electric field if loses energy, the wavelength will be longer and frequency will decrease. So that is the case. Okay. take a small break and then we will again continue. Then one more thing we will discuss on the parallel plate capacitor, that if there is a dielectric slab placed inside the parallel plate capacitor, then what will happen? So first of all, if the entire space is filled with a dielectric slab, it will be, capacitance will be just K times epsilon naught A by D. Previously it is C, now it is K times C. But if it is partially filled with a dielectric, then what will happen? This one is a parallel plate capacitor. This one. Now we consider that a dielectric slab is placed here. This one. Let us consider this dielectric slab has a thickness T, and this entire gap between the plate is taken as small d, and each plate has a surface area A. Total charge here given plus Q, here given minus Q. Now what will be the potential difference between the plates? Potential difference simply calculated by electric field into distance. Now see, in this vacuum portion, what will be the field? E. In this entire vacuum portion. But inside the dielectric, the field will change. What will happen to the field inside the dielectric? It will decrease by a factor K. So inside the dielectric, the field changes its value to E by K. So if you place dielectric, the field will always drop. Dielectric constant K, then in vacuum, if the field is E, then inside the dielectric field will be E by K. Now you have to calculate two potentials, one for moving the charge through the dielectric medium, and then for moving the charge in the remaining vacuum portion. So the total potential will have now two parts. One is for the vacuum portion and one is for the dielectric portion. Then for dielectric portion, what is the potential? E by K into T. For vacuum portion, what is the potential? E into D minus T. Their sum will be the total potential. In the vacuum portion, the potential will be E into D minus T. In the dielectric portion, the potential is E by K into T, because vacuum portion is this one. And what is the distance between this vacuum portion? D minus T. So E into D minus T is the potential for that vacuum part. And for the dielectric, potential will be E by K into T. Then you can write V equal to E taken common, it will be D minus T plus T by K. Okay? E is taken common. So you can write V equal to E common, D minus T plus T by K. Then what is this E for the vacuum portion? And for the vacuum portion we have already calculated sigma by epsilon naught. So in terms of Q and A, it will be Q by epsilon naught A. So write it, V equal to Q by epsilon naught A into D. I can take one T common, and then it will be 1 minus 1 by K. So if you calculate Q by V, you will get capacitance. Q by V is the capacitance now. So I can write directly that capacitance will be epsilon naught A divided by D minus T common into 1 minus 1 by K. That is the answer. If it is partially filled. Sometimes it is mentioned that 1/3 is filled with the dielectric. Then T should be equal to D by 3. Okay. Now from this we can check many things from this formula. So you have to remember this formula directly. So sometimes question comes directly from this formula, you can solve. Okay. Now see, if the entire portion is vacuum, then what will be the capacitance? Epsilon naught A by D. Now if some dielectric is inserted, there is something subtracted, means the denominator will decrease. Denominator increases means capacitance C will increase. So what we call that, if we place some dielectric, then capacitance will increase. So around the conductor, if you put certain dielectric, capacitance of the conductor will increase. Clear? If you put nothing, that is K is not there, because entire portion is vacuum, then it is epsilon naught A by D. Now insertion of the dielectric partially will subtract something from D. So denominator will decrease. Denominator decreases means C will increase. So capacitance increases if we insert dielectric in front of the conductor. Okay. Now check the other thing. Instead of dielectric, if I bring this one is a conductor. If this is a conductor, okay, this slab is a conducting slab, metal slab, you can consider. Then what will happen? Check. See, for conductor, what is the value of dielectric constant K? Infinity. It is infinity. So 1 by infinity will be 0. So it is D minus T, means no charge will stay at the bottom, all the charges will go to the top surface of this conductor now, because now this slab is conducting slab, this is not dielectric. So the charge will not reside at the bottom, it will reside here. So the effective gap between the two plates will decrease, epsilon naught A by D minus T. So the capacitance will increase. So insertion of the conducting slab will also increase the capacitance, because this 1 by K will be 0 for the conductor, then it will be only D minus T. So still it is subtracting from D, so denominator is decreasing. Denominator decreases means capacitance will increase. So in placing a dielectric, capacitance will increase. In placing a conductor, another conductor, capacitance will also increase. Remember this one. So if there is a conductor and we want to measure its capacitance, then if you bring a dielectric in front of and put it in front of the conductor, then capacitance will increase. If instead of dielectric you put another uncharged conductor, still capacitance will increase. In both the cases capacitance will increase. Okay. Now I will discuss one more point from this, that is the spherical capacitor. For the spherical capacitor, you can directly remember from this one. This one, we consider the inner sphere has a radius small r, outer sphere has a radius capital R. In the surface of the inner sphere there is positive charge plus q. On the surface of the outer sphere there is negative charge by an amount minus q. Okay. Then what is the capacitance? First we have to calculate the potential difference. The potential difference will be 1 by 4 pi epsilon naught, that is q by 4 pi epsilon naught small r minus q by 4 pi epsilon naught capital R. Okay. For the positive sphere, you can consider for the spherical distribution that all charges are concentrated at its center as if it is a point charge. So that calculation will be much more easy. So it will be q by 4 pi epsilon naught r for the positive charge and minus q by 4 pi epsilon naught capital R for the negative charge. Then I can write V equal to q by 4 pi epsilon naught common. So it can be written as without this one we can also write 1 by R minus 1 by capital R. Okay. Then capacitance Q by V is C. So C can be written as 4 pi epsilon naught divided by 1 by small r minus 1 by capital R. If you wish, you can calculate the LCM and put it upward. That is also possible. Or you can keep at this step also. So capacitance of the parallel spherical capacitor will be this one, 4 pi epsilon naught divided by 1 by r1, 1 by small r minus 1 by capital R, where small r is the radius of the inner sphere or positively charged sphere, that is inner sphere, and capital R is the radius of the outer sphere, which is negatively charged sphere. So same thing, this V is the work done in taking a unit positive charge from the surface of the negative sphere to the surface of the positive sphere, the same as before. As the charges are going one by one, this negative sphere will be more and more negative, positive sphere will be more and more positive until the dielectric breakdown occurs, because every surface has a maximum capacity to store charge. Beyond that it is not possible. Now, what is the capacitance of an isolated sphere? Isolated conducting sphere. What is the capacitance? Isolated sphere means there is only one sphere. Then the negatively charged sphere you can consider to be at very long distance. Long. How much long? At infinity. So radius of the outer sphere, if you set to infinity, then we will get the capacitance of an isolated sphere. So I write C isolated, that will be equal to 4 pi epsilon naught R only, because for this calculation you have to set R tends to infinity. Means negative sphere or outer sphere you can consider at infinite distance. Then you can consider that this sphere is a single sphere called isolated sphere. So this is the capacitance of an isolated sphere. 4 pi epsilon naught r. Okay. Now, can you tell me, if I want to prepare an isolated sphere of capacitance 1 farad, is it possible or not? If I want to prepare an isolated sphere, isolated spherical capacitor of capacitance 1 farad, not possible. Why? No, what is the problem in preparing that? Yes, yes. Yes, its radius then will be greater than the radius of the earth. You cannot prepare this kind of a spherical capacitor. See, why? Because C isolated you are claiming 1 farad. And this value, this is the C isolated we are claiming. So this is 1 by 4 pi epsilon naught, that is equal to R. So what is the value of R? 9 into 10 to the power 9 meter. Your Earth's radius is only 6.00 kilometer, and it is almost 9 into 10 to the power 6 kilometer. So on the Earth it is not possible to prepare an isolated sphere having capacitance 1 farad. It will be much larger than the Earth. Okay. Now, I consider two isolated spheres. One is this one, it is mounted over an insulating stand. It contains charge Q1. Another isolated sphere is there. It may be of different shape, different size, maybe Q2. It is mounted also over an insulating stand. Means insulating stand means charge cannot go to the earth. Now we will mention that its surface potential is V1, its surface potential is V2, and it is mentioned that V1 is greater than V2. Capacitance for this one is considered as C1, capacitance for this one is C2. Okay. Now, by a conducting wire, I connect both the spheres. Now, by a conducting wire, I connect both the spheres. Okay, like this. What will happen? I consider here the flow of positive charge is allowed. So positive charges will flow from high potential to low potential. Positive charge, because electrons are negative charge, they are flowing from low potential to high potential. Positive charges will flow from high potential to low potential. And remember, if you consider positive charge, then current always flow from high potential to low potential, and electron goes from low potential to high potential. But positive charge goes along the direction of current. So if you consider positive charge, then current and positive charge both go from high potential to low potential. If you consider current and electron, then current goes from high to low, whereas electron go from low to high. I here consider the flow of positive charge. So positive charges will flow from high potential to low potential. How long this flow continues? until the potential difference becomes 0. Means both will be at same potential. So finally, when equilibrium is reached, the surface potential for this one is V, surface potential for this one is also V. Then the sharing of the charge will be stopped. Okay. Now consider at this moment, suppose first sphere has charge Q1 prime, it is changed after sharing. Second sphere charge will become Q2 prime. Okay. So first sphere loses some charge, second sphere gains that charge. So first sphere's charges amount is now Q1 prime, and for the second sphere the charge will be Q2 prime. Then what will be the capacitance of them? C1 prime, C2 prime? No, it will remain C1, C2, because capacitance does not depend on charge and potential. So it will remain C1 and C2. Now can I write this one? Check. Q1 prime plus Q2 prime equal to Q1 plus Q2. If I can, then on the basis of which? Law of conservation of charge. Because charge is only shared, it is not created or destroyed. So previously initially what is the total charge of both the spheres? Q1 plus Q2. Now after equilibrium is reached, the total charge will be Q1 prime plus Q2 prime, but the sum of the charges will remain same. That is for the conservation of electrical charge. Then I can write that this Q1 is equal to C1 V1, this Q2 equal to C2 V2, C1 V1, C2 V2, because Q equal to CV. Similarly, this Q1 prime I can write, this is equal to C1 V, means after connection it will be C1 V. Second one is also C2 V, C1 V plus C2 V. Then we can write V equal to C1 V1 plus C2 V2 by C1 plus C2. C1 V1 plus C2 V2 by C1 plus C2. See, it is almost similar to the center of mass formula. Very similar to the center of mass formula. M1 M2 by M1 R1 plus M2 R2 by M1 plus M2. So this is the equilibrium potential. So if two capacitance are given and their initial potentials are given, then you can directly use this formula to calculate the equilibrium potential. Now, initially when there is no connection, what is the electrostatic potential energy of each capacitor? That I can calculate by using the formula half CV square. See, before connection is made, for the first sphere, what is potential energy? Half C1 V1 square. For the second sphere, half C2 V2 square. So this is the initial electrostatic potential energy, UI, before connection is made. Okay, so half C1 V1 square plus half C2 V2 square. Now When the connection is made and equilibrium is reached, then potential energy of the first sphere will become half C1 V square plus second sphere half C2 V square. Half C1 V square plus half C2 V square. Okay. Then it will be actually half C1 plus C2 into V square. So previously electrostatic energy before connection was made, electrostatic energy, total electrostatic energy of two spheres will be half C1 V1 square plus half C2 V2 square. Now once the connection is made and equilibrium is reached, after that potential energy of the first sphere will be half C1 V square and potential energy of the second sphere will be half C2 V square. So I take half and V square common, it will be half C1 plus C2 into V square. Now if I calculate this one, Uy minus Uf, this will be electrostatic energy before connection and after connection. Is there any change in electrostatic potential energy? Before connection, after connection, is there any change in electrostatic potential energy? Electrostatic potential energy is conserved. So conserved means remain, but it will not remain same. If you calculate this one will be non-zero, means greater than 0. Means initially it is more, finally electrostatic potential energy decreases. Now you will say that, sir, you are saying what? Because we know that electrostatic potential energy is a conserved, electrostatic field is a conservative field. So there should be electrostatic energy conservation. Now you are saying that electrostatic potential energy is decreasing, means it is not conservative field. So what happens? Normally energy conservation is valid in electrostatics because electrostatic force is a conservative force. But here I am saying that initial potential energy is more than final potential energy. That means electrostatic potential energy is lost, but it is converted to then other form. Lost means it cannot destroy it, it will be converted to some other form. That's why conservation of electrostatic potential energy is not there, but total energy is still conserved. So it is converted to some other form, that's why it is not equal. Now you have to identify which one is that form. It is converted to heat. Now you will say how heat will be produced. You forget one thing.